Good evening, everybody. It's a pleasure to have today one of us, Achilleas Porfyriadis. Achilleas has been in the department for a bit more than 3 years, but I'd like to say a few things about him since he's relatively young compared to other people in the department. Achilleas did his undergraduate at MIT. He did his PhD at Harvard with the Strong Chair. He did a subsequent postdoc in Santa Barbara, and then since he liked Harvard so much, he went back as a postdoc to the Black Hole Initiative at Harvard, and that's where we caught him and we brought him here. He's very well known, in fact, for some of the things he's done, and he has done very important and well-known work, in fact, in the theory of perturbations of black holes. And today, he will tell us about a very interesting and extreme subject, which has to do precisely with a new kind, an unusual kind of black holes and their dynamical evolution. Achilleas.
Yeah, thank you. Thanks. Indeed, it's been 3 great years. Let's hope for a lot more. Okay, so today I'm going to tell you about dynamical extreme black holes. Since this is a colloquium, I will go slow, relatively slow. There will be a lot of pictures, very few short equations, and one piece of art. Okay, so let's start. What is a black hole? So here's a definition. Black holes are, I'm saying, extreme states of space and time that represent physical conditions under which nothing can escape from behind the surface, which we call the event horizon. Okay, so people who've taken general relativity last semester will recognize this definition, basically. Notice that there is no mention of singularities here. The important thing is the event horizon. And the best way to understand what this sentence means in the causal structure of the space-time is to draw this type of diagrams, Penrose type diagrams, in which, generally speaking, time progresses to upwards. Every point, let's say, on this diagram represents, if we're talking about a spherical symmetric space-time, a sphere. But time exists, it moves upwards, and very importantly, lines which are at 45 degrees, like this one, are light lines. So they connect points which are distances which can be traversed by light. On the other hand, if you have a massive object, if you are the Earth, if you are light or something like that, you have to move on a time-like trajectory, because you have to move at the speed less than the speed of light. So you have to move along this type of curved trajectories. So an event horizon is something like this. So when there's a surface like that, notice that it is null, by the way, so the event horizons are null, which separates the exterior from an interior region, in the sense that in the exterior region, no matter how long you wait, so suppose you are traveling on this time-like trajectory, moving upwards, your time moves upwards, but your time-like, so this is your trajectory, and you wait as long as you can, and yet, if something happens here, it reaches inside the black hole. So that really summarizes what the black hole is, this diagram here. LIGO, which flies, let's say, very far from black hole, is on this trajectory. On the other hand, if I'm relatively close to the horizon, I'm following this type of trajectory, coming closer to the horizon, but still remaining outside of it. If I would have to cross the horizon, then it would be a time trajectory like that. Now, black holes are very interesting in the sense that they're described by solutions of the Einstein equations, which are very simple, even though they can be produced by very complicated matter collapsing. So the black holes that are relevant for astrophysics are described only by 2 numbers, their mass and their angular momentum. There's an exact solution called the Kerr solution, which describes pretty much all of the black holes observed by LIGO, by the Event Horizon Telescope, etc. There is a poor theorist version of these rotating black holes, which are spherically symmetric, where you replace the angular momentum with a charge, the electric charge. These go by the name Reisner-Nordstrom black holes. And so all of the equations I will present today will be, nearly all of them, will be about this type of spherically symmetric black holes because it's easier to deal with them. Okay, so, but what are extreme black holes? So remember, the title says dynamical extreme black holes. We kind of know what the black hole is now. We should also say a few things about what is an extreme black hole. Well, in one sentence, a black hole is extreme if it has the maximum theoretically allowed value of charge or spin for its mass. There is a maximum theoretical allowed value. If you put in charge which is more than this maximum, then you don't form this horizon. This horizon doesn't exist, so you don't have a black hole. Okay, why should we care? Should we actually care about extreme black holes? Well, yes, for various reasons. The first reason I'm saying here is they are actually observationally relevant because astronomers are telling me that they observe many black holes which are spinning very rapidly. So spinning very rapidly means approaching the theoretical maximum of allowed spin for their mass. But they're also fascinating theoretically from various points of view. So for example, right now in the high energy physics theory literature, there's a lot of fascination about the fact that people realized that these extreme black holes or near extreme black holes, they have quantum fluctuations near their horizon, which cannot and should not be ignored. And that leads to all sorts of conceptual breakthroughs. Also, mathematical physicists are very interested in these extreme black holes because they have various properties, the instabilities, but also stability results. So there is things they can prove about nonlinear stability of this type of solutions with actual instability features, which are weak enough that allow for interesting theories. So let me go over point number 1 first, which is obviously not my expertise, but I like to read these abstracts. So here's an abstract from a review 5 years ago on measurements of black hole spins. And I'm reading here that many accreting supermassive black holes are found to be spinning very rapidly, and the same is true for stellar mass black holes. Okay, so rapidly, very rapidly, just how much rapidly? So I love this picture. So this is the supermassive black holes measured with one of the methods by these astronomers. The takeaway message is, so ignore the horizontal axis, this is just the various masses of the black holes observed. Look at the vertical axis, which is the spin. Here, number 1 is the maximum theoretically allowed spin. So that would be an exactly extreme black hole here. And notice that there is a lot of stuff here and almost nothing down here. So there's a lot of white space here and a lot of stuff over there. So great, I love that. I mean, this is fantastic. This means that for some reason, these astronomical measurements are yielding a lot of very, very highly spinning black holes, which are actually very close to being exactly extreme. Now, I've shown this before, and I think also in this audience, and astronomers always will debate this. And this is one method, this X-ray diffraction method. There's other methods, continuum fit, etc. All of these observations happen in the electromagnetic window, and so there's a lot of uncertainty. So, in other words, astrophysics is kind of messy, so maybe this isn't really to be taken that seriously. I mean, it's good enough for a theorist, but if you delve into it, maybe it's not that trustworthy. And by the way, in this abstract, I cut it off here 5 years ago. This abstract continued, and it said that gravitational wave measurements of spin always yield moderate spins, I would say, something like 0.7 of 70% of extremality. But that's no longer true. So this event that Maria also mentioned last colloquium, this event was recently announced in July, which says there are 2 heavy by LIGO standards black holes of the order of 100, but also very highly spinning. So now these are not 0.7 anymore. One of them is claimed to be 0.9 and the other one 0.8. The reason I love this measurement is because this is in gravitational waves. So all of the messiness of astrophysics has gone away, and this is hard to argue with. And the idea is that most likely, as we keep measuring spins with gravitational waves, we will get more and more events like that. So it appears that highly spinning black holes are out there in the sky. Our best chance to probably observe very black hole dynamics very near extremality is likely with these extreme mass reaction spirals by LIGO. These are still intermediate mass black holes. They have high spins, but supermassive black holes are likely to have very high spins as well. And extreme mass reaction spirals are going to be a lot of events in LIGO. So if we are likely to have a very highly spinning supermassive black hole, we're going to observe it. Okay, so enough for observations. I mean, that's all I know about observations anyway. So let's move on to a little bit of theory. So let's start with this paper. This is a seminal paper on the 4 laws of black hole mechanics. There are 4 laws here, which are labeled 0, first, second, and there's a 3rd law as well. The 0th order law says that for stationary black holes, the surface gravity, this kappa, is constant. So you can think of the surface gravity as, roughly speaking, measuring the acceleration of gravity on the horizon as measured from infinity. That is constant. This is a classical result proven by these people. Also, if you have various black holes in the phase space of solutions, and you vary their masses, their angular momentum, the area of those black holes, the area of the event horizon of those black holes, obeys a first law like this. So this is also something that they prove. And then also there is a second law that the area always increases. So no matter what kind of process happens, as time goes on, the area of a black hole does not decrease. And so they say here in the abstract that two of these quantities, the area A and the surface gravity kappa, have close analogy with entropy and temperature respectively. And then these laws have close analogy with the laws of thermodynamics. Now this was an analogy back then, but then it soon became a real thing. So Hawking in 1974 proved that black holes are thermal objects and they radiate at this Hawking temperature, actually given by the surface gravity divided by 2 pi. Which means that in this first law, we should interpret the black hole having an entropy, which is given by a quarter of its area. And that also became a reality, at least as far back as 1996, when Strominger-Vafa derived that this number of microstates for black holes can be obtained from counting literally states, microstates of solutions in string theory. So by this time, black holes are not, the laws of black hole mechanics have become laws of black hole thermodynamics. Black holes are understood to be quantum objects having this temperature and carrying entropy, a large number of entropy. Now there was a third law in that same paper with a slightly different status. So you can read here, this is how their paper ended basically with the third law. They said, extending the analogy further, we could postulate that there is a third law, which is the following. It is impossible by any procedure, no matter how idealized, to reduce kappa to 0 by finite sequence of operations. So in thermodynamics analogy, this would mean it is impossible to reach absolute zero temperature. But they say this law has a rather different status because it has not been proven mathematically. They went on, of course, to say that, however, it is well motivated, etc. Now, this third law of black hole mechanics has been disproven. So there's this recent paper by these mathematicians where they showed that they can form exactly extremal black holes by collapsing in appropriate matter in finite time. So in some idealized way, etc., they can form such a black hole and they can even pass through a non-extremal black hole initially, so reducing basically the temperature from something finite to exactly 0. So that third law of black hole mechanics has been disproved. And so now the status of external black holes is not that they are impossible to come by in general relativity. They can be made. Now, let's also discuss something else. They have these interesting instability features, which was discovered by another mathematician, Artakis, in 2011, where he said he set out to show stability of black holes. And so the simplest thing to do first is to consider a perturbing field. So you have an extremal black hole background, and you put a little bit of perturbation of some field on top of it. Let's take that field to be, for example, scalar, although his results have been generalized for all sorts of perturbations. It satisfies some equations of motion, this wave equation over here. And he showed that indeed, as time goes on, the scalar field decays everywhere on and outside the event horizon. However, he also discovered, somewhat surprisingly, that transverse derivatives, so derivatives that are in the direction transverse to the horizon, sufficient number of transverse derivatives, if you take sufficient number of transverse derivatives, they don't all decay on the horizon. And if you keep taking derivatives, they begin to blow up as time progresses. So exactly on the horizon, there is no decay and there is even blow up. So that's an instability, but it's a linear instability because this is a linear result. And so that raised the question, what's the fate of that instability if you allow the perturbations to back react on the background? And now, this perturbation allows for the gravity to come in, and you have the full nonlinear system of, let's say, the scalar with the Einstein and Maxwell, in this case, for example, field. So this nonlinear theory is hard to solve, of course, and it has been studied numerically to figure out two things. First, does the linear instability survive in the nonlinear regime? And second, well, yes or no, so does it exist or not? And then also people would like to know what's the endpoint of this instability. And so you will see that the answer is slightly intricate. The answer is basically yes to all of these questions. So this paper numerically studied the fate of the linear tax instability. So they put in a neutral scalar, so as a Prof. So this is a scalar field that doesn't have any charge. They put it on an extreme Rystad-Nordstrom background, those spherically symmetric charged black holes, which were made extreme. And they said, okay, if we let the scalar field back react on the geometry, what is going to happen? And they confirmed what you would expect that normally happens, that you're adding some energy to the black hole. So generically, gravitational back reaction will regulate the instability in the sense that the whole system will settle down to a sub-extreme, final temperature Rystad-Nordstrom black hole with a surface gravity that is of the order of the small perturbation that you put in. Okay, but that doesn't mean that the instability is not there in the nonlinear theory, because it is still there in the transient sense. So the nonlinear theory still has the instability, but it occurs for a long time, but that is non-zero, and it reaches a finite value. So if you dial epsilon, the instability doesn't completely go away. So the instability is there in the nonlinear theory, but it becomes transient. Okay, so that's the generic situation. Now, there is also a non-generic situation that these people observe numerically, and they dub this solution a dynamical extreme Rystad-Nordstrom black hole, which I will call DERM for simplicity. So these are some fine-tuned setups where you evolve this system of Einstein equations coupled to Maxwell, coupled to this neutral scalar, this whole nonlinear system. You evolve it, and what you find is that at the end of the day, asymptotically in time, for as long as the numerics can run, of course, the metric, so the space-time metric, tends to that of a standard static extreme Rystad-Nordstrom black hole, of the thing that was, for example, the background in the linear story. So, okay, the metric does that, but the scalar exhibits the same behavior as the linear R-type scalar exhibited without ever settling down. So it doesn't dissipate, it exhibits this instability on the horizon of that nonlinear now solution ad infinitum. So this is to say that this is a very special solution, which at late times looks basically like a dynamical extreme horizon with a static exterior. So the exterior is a standard static extreme Rystad-Nordstrom, but the horizon is dynamical. It has this Arietakis thing evolving on it ad infinitum. Okay, so that was a numerical conjecture, and you can ask, are these solutions real? And mathematicians especially would like to ask, can we prove stability of this type of solution? So if we have initial data which are close to this type of, to the original, let's say, extreme Rystad-Nordstrom, can we make sure that in an open neighborhood of initial data close to that point, the endpoint of the nonlinear evolution will be this type of things always? And indeed, such a thing was proven recently by these mathematicians. Well, they put out a paper which is not published just because it's math, not published yet, I think, and they proved nonlinear stability. So there is a proof of a stability of these solutions in this codimension one sense. I will explain what that means very soon. So it's a proof assuming spherical symmetry, codimension one, which I will very shortly explain. But also they conjectured that what happens in the numerics is likely to be also generally true. They conjectured that this type of dynamical extreme solutions lie on the threshold of black hole formation. So for initial data which are about to form a black hole, and whether the horizon forms or doesn't form is a threshold. On that threshold, these dynamical extreme black holes lie. So the picture of the initial data space is like this. So this is called the moduli space of initial data. And they propose that this is the general picture. So, okay, the Einstein-Maxwell scalar equation are a set of coupled nonlinear PDEs, right? So there's a lot of work to be done, but it can be formulated as an initial value problem. And you can think of this entire rectangle as, depicting sets of initial data, consistent initial data, which you can evolve in this PDE sense and see what kind of solutions have. So this point here, for example, would be initial data that evolves to an exactly static extreme Reisner-Nordstrom black hole, a vanilla solution. On the other hand, there is data which doesn't form black holes. They are on this right-hand side. They call it dispersive data. So points from here evolve to black holes, to spacetimes which don't have an event horizon, so they're not black holes. Everything just disperses. You end up with Minkowski spacetime, flat spacetime. On the other hand, points on the right generally produce sub-extremal black holes of some finite temperature, finite surface gravity. So these gray points here produce not this extreme Reisner-Nordstrom, but some sub-extreme Reisner-Nordstrom everywhere. Now, these lines here are supposed to show you various sets of initial data, all of which produce some sub-extremal Reisner-Nordstrom of some charge-to-mass ratio R, which is less than 1. So 1 would be exactly extremal. Less than 1 is a sub-extremal black hole. And if you want, let's say, a sub-extremal black hole of charge-to-mass ratio 1/2, there is this line of initial data that will do this. Now, this red thing is the line of exactly extremal space-time matrix, which they proved is a stable line just like the other ones. And they also conjecture that it delineates, this moduli space of initial data. So it sits exactly at the boundary of dispersion from black hole formation. These black holes, unlike this point, everything else on the red line, will be of this dynamical sort. So there will be the matter here, let's say the scalar, which will be behaving like this linear type paradox instability. So this is the line of Ders, basically, the red thing. An important thing to notice is that from this point of view, making such an extreme black hole isn't harder than making a sub-extreme black hole of some other fixed charge-to-mass ratio. So in the old days, people used to think that, extreme black holes are some edge case. In fact, on the other side, it might be that naked singularities lie. This is not true. And they're hard to make, etc. All of this in light of the violation of the third law of black hole mechanics and the fact that on the other side here you have dispersive solutions is nowadays no longer believed. Making one of those dynamical extreme Reisner-Nordstroms is no harder than making one of those from the point of view of collapsing initial data in the partial differential equations. So, okay. Let me now say a few things about, so all of these people, numerical relativists and mathematicians, they do this type of exercises in full four-dimensional physics, in full generality. That's why the mathematical papers are very long and the numerical papers require a lot of expertise. But we know in the high-energy physics literature that whenever you have a black hole which is close to extremality, sufficiently close to its horizon, there is the emergence of this two-dimensional anti-de Sitter space. So ADS2 and near extreme black holes is the title of the slide. The statement being that near the horizon of extreme and near extreme black holes, space-time is always ADS2-like. So the simplest example would be this, for example. If you have the standard static extreme Reisner-Nordstrom or standard near extreme static Reisner-Nordstrom, the near horizon of space-time is described by this metric. Now, I realize many of you have never seen a metric. So, okay, don't be offended by this. Think of this as telling you what's the distance between 2 points whose coordinates differ by dt, dr, and there's a d theta, d phi here. So on the plane, for example, in Euclidean geometry, you would say by Pythagoras' theorem that the distance is ds squared is equal to dx squared plus dy squared. In 3 dimensions, you would add plus dz squared. If you do special relativity, you realize that you have to add dt to the picture on the same footing. You add it with a minus sign, minus dt squared. And then by the time you graduate to general relativity, you realize that the coefficients can't be constant anymore. You can have functions of the coordinates as coefficients. So this is such a thing. It tells you what's the distance for a space-time that describes physics where time and space are treated equally and there is curvature. This part here is the ADS2 part. This is the metric of the ADS2. Now we know in high energy physics that the gravitational dynamics of this type of near horizon ADS2 throats, as we call them, is nearly decoupled from the far asymptotic region. And we also know that it's governed by some effective 2D theories. So 4D gravity within, let's say, spherical symmetry reduces to some effective 2D theory of gravity, the most famous one of being the Joukis-Teitelbaum theory. The nice feature of this theory is that back reaction, the nonlinear part of the problems we've been discussing, whether it's about classical back reaction or quantum back reaction, is often solvable in these 2D theories, like solvable by doing analytics with a pen and paper. So this allowed, for example, currently in the HEPTH literature to find some very interesting results on what quantum mechanical fluctuations in these throats imply. So one big result, for example, is that it implies that the Bekenstein-Hawking entropy, this entropy that I said is associated with all black hole horizons, as the temperature goes to zero, that entropy diminishes. So this is what you would expect normally from a quantum mechanical system, that the temperature goes down as you dial the temperature down. But previously, for supersymmetric black holes, the Strominger-Vafa result, for example, that I showed before, would imply that even for an exactly external black hole at t equal to zero, you have a large degeneracy of states at t equal to zero, and therefore you would have a non-zero Bekenstein-Hawking entropy equal to the quarter of the area. So that puzzle is being resolved now by the fact that people understood better the non-supersymmetric case by studying this type of Joukis-Teitelbaum theory in 2 dimensions and its quantum mechanics. Another puzzle that is being understood right now is the fact that at very low frequencies, so for quanta of very low frequency, the Hawking emission is no longer exactly thermal. It's another recent interesting result. Okay, but for the rest of the talk, I will set h bar to 0. So what this story also told us is basically the fact that t goes to 0 and h bar goes to 0 are 2 limits which don't commute. So ultimately, you have to consider black holes which are near extremality quantum mechanically for these reasons, for example. But for the classical story, for the solutions, let's say, that the mathematicians are talking about, what this means is that you have to send h bar to 0 first and then t to 0. And that's what I will do from now on, I think, till the end. Okay, so here is the paper I want to talk about. Let's see, how much time do I have? Okay. So we put out this paper very recently with Chris Rosen, who is a senior researcher here in the department, and Yorgos Sartzidis, who is a senior undergrad in the department. So in this paper, what we did is we wrote down an explicit closed form description, so formulas, explicit expressions, using this effective 2D type of theory, the JT gravity, which describe the late time near horizon approach to such Dern black holes. So the stuff that people either discuss numerically or prove theorems about now has explicit formulas behind it. So let me give you a flavor of about how this comes about. So here are some more Penrose diagrams. So these would be Penrose diagrams of the eternal version of a static Reisner-Nordstrom black hole. So on the left, this thing here, for example, is a black hole. So previously I drew, on the first slide, I drew the Penrose diagram around this point, right? And this is the event horizon. This is some near horizon surface. This is the infinity. And I drew this part, so this is a black hole. As far as people who are here in the exterior, this is a black hole. Now this is a static black hole, so it goes infinitely up and down. That's why you see it periodically identified like that. The left picture is the exactly extreme static Reisner-Nordstrom. This is the sub-extreme some finite temperature rise and Nordstrom, but we're assuming it is close to extremality. And this is what you would call a super extreme rise and Nordstrom. This doesn't have a horizon. Notice that this doesn't have any matter. Now, the statement that I made before that ADS2 arises in the near horizon region is the fact that in this blue shaded region, for example, which is near that horizon, the geometry is ADS2-like, and the corresponding Penrose diagram of ADS2 is this. So ADS2 is like a box, so that's what the two vertical lines are on this picture. They're the two boundaries of ADS2, and this blue region is identified with this blue region of the global ADS2 geometry. And similarly, in the near extremal case, there is again, an ADS2 which arises. It's just a different patch of the global thing. So this is roughly speaking in pictures how and why we're saying that ADS2 arises in the near horizon or the portions of black holes. Okay, so what we did in that paper is, we basically realized this. So on the left-hand side, you imagine that you have set up initial data on a pair of light-like surfaces, which we're calling here sigma 1 and sigma 2. And that initial data, when we evolve it upwards in time in this picture, produces this type of dynamical extreme rise and Nordstrom black hole. So this is supposed to represent for you pictorially a dynamical extreme rise and Nordstrom. Here is its horizon. Here is infinity. If you are in the exterior of the horizon, so to the right of that line, then you don't get any signal behind this horizon. And this blue shaded region here is the near horizon and late time portion of that dynamical extreme solution. That's what this blue shaded region is supposed to mean. This curvy line here is some constant radius line away from the horizon, so a little bit outside the horizon. It's basically like these lines on the static solution. And we think that this blue shaded region can be described in ADS2. So there's an effective theory of this blue shaded region given by J. type of gravity, for example. And what we have to understand is basically how things get glued here on this line between the near horizon, which is ADS2, and the far region, which is different. But the numerics and the mathematical proofs are telling us that in the exterior, away from the horizon, far away, things settle to the static extreme rise and Nordstrom. So that's not very difficult. All of the dynamics is happening in this blue shaded region. So we go to this picture, the ADS2 picture, and we try to find what are the correct boundary conditions on this boundary B. So this boundary B, you should think of it as corresponding to this line here, this curvy line here, which is some near horizon line. So the point of the exercise becomes find the correct boundary conditions on this B, which which gives you the desired behavior of the nonlinear 4D solution. So here on the right-hand side, the theory is an effective 2D theory. Now we work with the JT gravity here because we have spherical symmetry, we have a massless scalar field. And in that theory, things are very simple. So the metric is always fixed to be ADS2. So this is the ADS2 metric I wrote before in TR coordinates. It's also good to write it in these other double light-like coordinates U and V, which are shown here, such that this horizon, for example, is a constant U line. The metric is fixed to be always that, despite the fact that there's gravitational dynamics. The massless scalar perturbation that we put in, which has to satisfy this wave equation, can be solved very easily. It's a superposition of two arbitrary ingoing and outgoing functions, f and g. And in this J-Keefe-Katterbaum theory of gravity, all of the gravitational dynamics is encoded in another field. Another field that's called the scalar dilaton capital phi here. And what this field measures is basically how the radius of the sphere that is transverse to S2 changes as you move outwards from this ADS2 region to the exterior, far away to the asymptotically flat region. That's what this dilaton measures basically. And the solution for it captures the entire gravitational dynamics within spherical symmetry of this 4D theory. Here's another picture to say the same thing. So you are probably more familiar with pictures like that. So less familiar with Penrose diagrams, but more familiar with this type of picture. This is also supposed to denote or depict for you the near horizon region down here. So this is an embedding. Let's say you take a constant t slice, so there's no time in this picture. This is a fixed time. And then the spatial metric, whatever space remains, you embed it in R3. And then, the black hole will look like this, this type of thing. So the horizon would be down here. I'm drawing a circle for the horizon, even though it's a sphere, just because it's easier to draw circles. So one dimension is suppressed. And then there is this near horizon region. And here out there, this is the asymptotically region where things become flat. So that's what the flattening there is doing. So the dynamical extreme right hand northern is something we said that has a dynamical near horizon part. So this part here is supposed to be a dynamical throw. And it is described by this type of effective 2D theories like J-Keefe tidal concavity. Whereas the far part is basically static, exactly extreme right and north. And then there is the transition region. This transition region is the thing I'm calling in this picture the boundary, or it's that line over there. So this is another way to describe the same thing. If this was a video, then this part would be evolving. This would be the dynamics, and this part would be basically staying still, being the extreme right and north. So okay, here's a piece of art. This is the one long equation, but it's in a frame, so it's fine. Take it as being just a piece of art. The point being that you just appreciate that it exists. You don't try to parse it too much because then all the fun breaks down. The actual point, of course, is that I want to make sure that you appreciate the fact that there is an explicit solution in closed form that you can write down. So let's discuss a little bit how to get that solution. As we said, what we need to do is we need to understand what are the boundary conditions in the region that is a transition region between the near horizon and the far part. So in the far, there is basically the static extreme right and northern exterior. So in this picture, this means that the dilaton at late times here should reduce to a dilaton that would correspond to what we call the vacuum dilaton for exactly extreme right and northern, the static one. So we arrange for that as far as what this dilaton phi is doing, this degree of freedom of 4D gravity that measures the deviation of the size of the S2 the size of the sphere as you begin moving outwards. On the other hand, the fact that the matter, the scalar, for example, the neutral scalar that we put in, has to behave like Arietakis ad infinitum means that we have to impose some conditions on F and G, basically. Remember, the solution for the scalar is basically the superposition of F and G. So there has to be some condition on F and G, and the condition can be written as follows. So if you call delta T the net flux of that scalar matter sigma through this boundary, then you will ensure linear Arietakis behavior for this full solution if you impose that this delta T as you go again towards that point at late times, and its first derivative go to 0. So these two things will translate to linear type of Arietakis behavior for the nonlinear solution with the matter. And we find that the only way to have a solution with a black hole horizon is to have this delta T negative. So you have to have this outflux of scalar matter energy momentum tensor through the boundary towards the late time part. But other than that, if you have enough sufficient flux, more than some minimum value, you can create this solution. So to summarize things, the picture is like this. You have the 4D dynamical extreme right and northern. It exists. We knew that we had evidence for that numerically. We now know it also as a theorem in math. And what we did is we provided an explicit closed form expression for this near horizon late time portion of it in terms of this J-Keefe tidal equations of motion. We saw that we need to have this final burst of outgoing matter through this ADS2 boundary, therefore here towards the exterior, by imposing appropriate boundary conditions. Okay, so good. Are we done? Well, we're never done in physics. There's a lot more to do, of course. There's a very long to-do list. I put in 3 things here, but there is a lot of dots afterwards. So one obvious to-do thing would be, for example, to consider charge matter. So all of these exact results, both the numerics, the theorem, and our 2D effective description used neutral massless matter. Very recently, like last week, there is a numerical paper by Pretorius and a student of his, where they consider the situation with a charge scalar, and they claim that they can again produce this type of dynamical extreme solution. That's very interesting. On the other hand, you would also want to ask, what happens with pure gravity? So at the linear level, pure gravity also behaves like the linear Archimedes instability. Is there a dynamical extreme Kerr black hole? That would be fun. Now, as I said, the rotating case is a lot harder, so this is not so easy to attack. There's also the question of the third law for black hole thermodynamics. So what has been disproved is the third law of black hole mechanics. So within the classical theory, you can form a black hole in finite time. But the third law of black hole thermodynamics is really a quantum statement. So you would have to understand how quantum mechanics has to intervene when you're trying to form this exactly extreme black hole, and it has to intervene. So you would have to understand what's the what happens quantum mechanically to the Archimedes instability, both linear but also at this nonlinear level, and many, many more questions. So this is the end. Thank you.
Very much, and we are perfectly on time. Any questions?
I have a question regarding that graph that you had with the red line. Remember that one?
Yeah, this one.
Okay, on one hand, you have the experimental things that you showed from 5 years ago. And what I see here, I see a red line that corresponds to DERNs, and the whole sector on the left-hand side corresponding to any kind of black hole, and a corresponding sector on the right-hand side to no black holes.
Yeah.
So unless your DERNs have a heavy weight on them, I would say that they are fine-tuned to death. It's a set of measure 0 in this space.
Yeah.
And I cannot see how this is in agreement with the experimental stuff. You have to make them with fine-tuning of initial value data.
Yeah.
That's what this graph shows. How do you reconcile that with the experimental data you quoted from 5 years ago?
Right, so good. So what Nick is pointing out is that if you want to have an exactly extreme black hole, you have to stay on this red line. And that's saying that it has exactly 0 temperature, exactly 0 surface gravity. On the other hand, the experimental data, or the astronomical data, was giving us some small, sometimes, small temperatures, but finite anyway. That would mean some other point on this left-hand side. Now, regarding fine-tuning, so if the point is on this line, for example, suppose this line is all the black holes, which are...
What's this line?
This line would be, for example, a black hole with a fixed charge-to-mass ratio equal to R. So let's say a half.
Okay.
So this is a half away from being exactly extremal and half away from being the Schwarzschild one. So on this line lie all the black holes with charge-to-mass ratio exactly equal to 1/2. So that is also fine-tuned. So if you want to say, I want to make a black hole which is exactly 1/2 charge-to-mass ratio, that's fine-tuning as well. So from that point of view, the nice thing about this picture is that the exactly 0 black hole temperature is not more fine-tuned than the exactly 1/2, for example. That's one good thing about this picture.
But you're not explaining the astrophysical curve that there is a high density of them close to the red line.
Right, I'm not.
So there is a reason for what's the reason?
I'm not.
No.
I'm not explaining that. No, of course. But let me also say the following. So that's first of all a good thing, because in a few years back, people would think that fine-tuning things to get exactly to exact zero temperature is impossible, basically. And it's much, much harder to fine-tune things to make a 1/2 charge to mass ratio. So that's a good thing. Now, what's the bad thing? The bad thing is that, of course, fine-tuning is still fine-tuning. So even the 1/2 thing is fine-tuning. So you would say that, okay, what happens to black holes which are near extremal? Basically, this is the more physical thing to say. Initial data which evolves to black holes near extremality. And there, of course, I mean, mathematically, they're a bit less interesting because everything that is away from this red line here doesn't have this nonlinear stability with weak instability property. It literally becomes a stable, static sub-extremal Reisner Nordstrom everywhere here. But if you're sufficiently close to this red line, what happens is that for a long time, you evolve like this red stuff is evolving forever. So there's a transient version of all of this story. There's always a transient version.
The answer to this question is the calculation of Thorne from the 70s, right? That accretion usually brings you in that area.
Say that again.
Right. So the question is, if the question was, what explains that many black holes are roughly or nearly extremal? There are candidate explanations. I mean, some people will say that accretion disk physics tends to spin up black holes, and Thorne has an upper bound on that, which brings you close to this thing. No, I mean all of this stuff. When I say accretion disk physics, that means you have to know what's going on, really, what the matter is doing. It's messy, so it's always debatable. So all of these things are debatable. To the extent that fast-spinning black holes exist, so these are fast-spinning black holes, which I don't think are debatable because they come from gravitational waves. For a long enough time, they will behave transiently like the exactly extreme dynamical black holes that I talked about.
Okay, thank you.
There is currently a discrepancy between astrophysicists and gravitational physicists. Astrophysicists think that the spin is close to 1, yet from LIGO and all the merging, the spins that have been inferred are significantly less.
Yeah.
How do you?
That's true. So that's true. So at least 5 years ago, it was definitely true. There was another bullet point here which said what you just said, that from gravitational wave measurements, spins come about to be roughly 70% away from extremality, so 70%, 0.7, and not close to 1, whereas all of these electromagnetic wave measurements give very high spins like this. Yeah, I mean, obviously, these electromagnetic measurements have some kind of bias. I'm not an expert. I don't know why this method, for example, the X-ray reflection method, tends to give these very high spin results. I don't know what the reason is for that. But I would contend the fact that gravitational wave physics gives moderate spins. That's probably not true anymore. Do you consider 0.9 moderate? I mean, it's away from how much I would want it for as a theorist. I would want many 9s there after 0.9, but it's already way more than 0.7, which used to be the statement, and the tension seems to be going away.
Spin bigger than this, you cannot see with present day interferometers. You need the future ones that come.
There's also the question of what kind of templates they put in the gravitational wave detections. So the way they measure spin and the way they find signal in LIGO, for example, is they have to have a theoretical prediction for what the signal should look like. Otherwise, it's buried in the noise and you can't find it. There aren't that many templates of solutions that produce that involve near extremal black holes, because these are more costly to produce, and there's a crucial part of the template that can be done only numerically in all of these cases. So that's another question. So if you don't have enough templates, there might be way more signals in the gravitational wave data of highly spinning black holes, but harder to extract if you don't know the theory well enough. Yeah, but the direction seems to be good. So what used to be just all 0.7 is now more than that. This is intermediate mass black holes. And the reason I said this here is that supermassive black holes, I think there is consensus that it's very likely some of them are very highly spinning.
First, can I just make an astrophysical point? So these are intermediate mass black holes. We don't have very good ways to produce intermediate black holes made from collapse. So these black holes come from mergers. Even if you merge two Schwarzschild black holes, they will inherit some of the orbital angular momentum and they will spin up. In order to get to 100, probably you have been through quite a few mergers. And when you are talking about multiple mergers of stellar mass black holes, these angular momenta all tend to be in the same direction because they inherit the galactic rotation. So they will add up and they will spin up. There are astrophysical ways to spin them up very much.
Which is the same mechanism as the efficient.
Yeah, exactly. It's absolutely the same mechanism.
Increasing mass, right?
Yes, you are increasing the mass, but the relatives, if they all spin the same way, you have their speed and the angular momentum, the orbital angular momentum. So the per mass angular momentum goes up. If they all spin in the same way and the orbit goes the same way, and in a galaxy, if you have stars, everything will go the same way, both the orbits and the individual speeds. Now, for the supermassive black holes, it's totally an observational bias, because supermassive black holes, unless they are active and spinning, put differently, if they're spinning, they tend to shoot out jets, and jet black holes are easier to see. So, absolutely, they exist, but you will see them more also.
Very good.
Sorry, I apologize for my ignorance, but maybe you mentioned it in the beginning, but I missed it. Why is there a theoretical upper limit? You keep that slide. Why is there a theoretical the other one?
This one?
With the laws.
Yeah.
First
Okay.
one.
Yeah, so why is there a theoretical upper limit on the rotation? How does it come from the laws? Or what is the, I don't get it, where the limit comes from?
Yeah, it doesn't come from these laws. It comes from the fact that if you look at exact solutions of the Einstein equation, so you look, for example, at this Kerr solution, which describes a rotating black hole of mass m and angular momentum j. In order for you to call it a black hole, it has to have this causal structure that I'm describing here. There has to be this horizon. And if you naively plug in that Kerr solution, angular momentum more than the mass here, you don't get this horizon. The causal structure changes drastically. You get basically a naked singularity, which is a non-physical solution. So solutions of the Einstein equation, which include angular momentum, they have horizons, black hole horizons, and they're black holes only if the angular momentum is less than a value fixed by the mass. That's the reason. So these black hole laws are written down on this type of solution. So you have a family of Kerr black holes with some masses and some angular momenta. They have some area, and within that phase space, this is, for example, an equation that holds.
Okay,
But that phase space is a phase space of black holes. If you have a naive solution which is J greater than n, then there's no horizon. You can't calculate, for example, this delta A.
It's like if you add of 4 dimensions. 9 dimensions you can have because the spin is not bound.
What guards us against spinning them up too much? Do they?
People have tried. People have tried to spin up theoretically, I mean.
It's not something like, a hard thing like speed of light, right?
No, I mean, it's a conjecture. So at the end of the day, this goes by the name, the weak cosmic censorship conjecture of Roger Penrose, that you cannot cook up a situation that collapses in four-dimensional general relativity, that collapses and produces a naked singularity, which would be that type of solution that you're talking about. Or, starting with a black hole and throwing stuff at it in an appropriate way to overspin it. These things don't work because there's this conjecture, which has not been proven, but it's very much expected.
Okay. So there is no theoretical actual reason, right? I mean,
There are theoretical.
okay, there is mathematical theory or physical.
Mathematical theory. First of all, the conjecture is known to fail in very, very fine-tuned situations. So you believe it generically, but you can create from initial data, from regular initial data, naked singularities, and that was done already by Aristotle a long time ago. Second, these things eventually have been mapped, especially not that much the rotating one, but the reciprocal ones with the similar bound, have been mapped via ADS-CFT or mapping quantum systems, have been mapped to statements about Hilbert spaces, and there it's clear, if you violate that bound, lose your time. So it is indeed the bound.
Yeah,
it's
but
like-
you're assuming ATS-CFT. Okay.
Yes,
All
sure.
right, so
But this
that's
suggests
a
that the
conception
underlying,
that goes beyond the.
I'm giving
How
you
is-
arguments, yes,
This is not.
I'm not proving anything, I'm giving you arguments that this goes beyond gravitational equations.
Don't
and-
use ATS-CFT.
That's your problem. Anyway, the point is that
That's
there
the
might
thing
be
that's
other
there.
design reasons why such bounds may be there. Of course, there are also attempts that have been done eventually to construct these things, but always you can.
Let me just-
I think you can have some case, but they are indication.
Let me just add one more thing. It would be actually lovely if, something like that could happen out there in the nature. So in this paper, for example, there is a statement that they seem to be finding. So this is as of last week, so obviously, it's all under investigation. But they seem to be finding that on the threshold of making these extreme black holes, if you are on the dispersive side and you don't form the horizon, there are large curvatures. So nearly naked singularities that you can apparently see from far outside. So this is actually good news if you want to learn something about the quantum gravity, let's say very strong gravity, high curvatures, which you can observe from far away, not hidden behind the horizon. So if this type of thing, if cosmic censorship is wrong, and we can find an example, how it's wrong, and we can begin observing in the sky these things, would be wonderful. It would be great. It seems to be very hard to arrange for.
Yeah, but as you said, in order to observe them, you need to know what we're looking for. And
Exactly.
if there are no solutions, but it's just, conjecture, I'm sorry, but the conjecture is not good enough, right? To call it a theoretical upper limit.
Yeah. So my statement about the theoretical upper limit was actually kind of lowbrow statement. So it was about exact solutions. So the exact solutions like these Kerr solutions, they do have theoretical upper limit. But other solutions, which people do try, and as I said, I'm rooting for these other solutions to exist, could violate weak cosmic censorship, and we could observe these high curvatures out there in the sky. It would be wonderful.
That by you have perhaps spinning too fast, cannot come together.
Really, a black hole that breaks and rips apart space-time, and you cannot live.
Yeah, because
Sure, if you rip apart the space-time itself, right? What's the meaning of you cannot angular momentum? It doesn't matter, right? You've already broken everything.
What one sense?
So you keep adding, and it's still broken. It's still a black hole.
No, it's not a black hole, it's a naked singularity. Black hole.
Okay, it's a singularity. Right?
Well, a singularity eventually will have to get regulated by quantum mechanics. So it will. So this is an opportunity to observe quantum gravity. That's what I'm trying to say.
You see what I mean, right? You can keep pulling angular momentum and still you go.
That is my question, a practical question. So, as we said, you
Yeah,
keep
it's
merging, so
it's radiated way,
a
yes.
way to
To
keep it
make
down.
simulations radiated.
So, okay.
More questions.
You're the boss.
So without this frame R, it has maybe 2 dimensions, 12 feet. How does it look and what does it tell us about black holes?
Sorry, sir.
And this equation is very complicated for us to see a meaning. Like it's not a Gaussian, it's not a parabola. What is it? How does it look? What it tells us?
Right. So, as I was trying to explain, so this field phi here, it tells you, let's say in this picture, which you will appreciate, it tells you how the radius of these spheres, the circles in this diagram, grow as you move upwards from this throw. So it measures the size of this sphere.
It's obvious, but this is a time-dependent solution, right?
Yes, the whole thing is a time-dependent solution. So this picture is supposed to be a snapshot of that dynamical solution. And if I had the video, there would be a lot of evolution happening down here, but the thing would be relatively static up here. In this transition region, of course, there will be a transition, which is described by this solution. This solution, roughly speaking, measures the radius, if you want to say, the area of that sphere as you move away from the horizon towards the asymptotically flat region.
But it also measures how it moves back.
It also measures how it evolves in time because this is a dynamical solution. So these u and v are the two coordinates in two dimensions. One of them is time-based. So yeah, I mean, this is the nice thing about this being explicit is that you can begin studying it. You can use it for understanding how quantum mechanics has to intervene at appropriate places, etc. So you need to first have this type of analytic control over solutions to ask more complicated questions. There is a long to-do list here.
There was one last question.
It's a comment, in fact. You left open an issue that you introduced, which is the third law. And you said that it was proven that classically in gravity, the third law is not valid. However, in work that we have done recently, which you are very well aware of, we have good hints that in fact quantum mechanics is going to reinstate some sense the third law, because the quantum effects that in fact happen when you go very close to the extremal limit are such that they make the dynamics of these fluctuating black holes like a glass, and then all of the relaxation times are expected to go to infinity, and therefore you don't expect this eventually to. I think it will happen like in real world.
Absolutely, I agree. So that's why I said what has been disproved is the third law of black hole mechanics. The third law of black hole thermodynamics we still believe is true, and it is made sure to be true by the intervention of quantum mechanics. So absolutely. That said, I mean, okay, this is a recording. Anyway, that's why I did not underline this part from the mathematicians. I called this the disproof of the law of black hole mechanics.
Okay, Ram.
The end of the talk, you talked about the region approaching the horizon, transforming into dynamic.
Yeah.
Are there any experimental applications or behavior of that we can observe at large scales from this transformation?
Yeah, I mean, so that's obviously a very good question. So first of all, these dynamical extreme black holes outside, I mean, first of all, you have to be very close to extremality, so you need many nines, 0.999, etc., to begin talking about these exact solutions being relevant for observations. And also, if you stay away from the horizon, because this part is basically like static vanilla extreme black hole, you stay away from the horizon, it's very hard to have a proposal for an observable that you can measure. What you could do is if you cross the horizon, then there will be large tidal forces implied by these instabilities, these weak instabilities, and those are detectable, of course. So if you cross such a dynamical extreme horizon, there will be something very observable to you. But if you stay outside, it's kind of hard. Nothing really signals that strongly here. That region is basically like vanilla static extreme black hole. But it's a very good question. I mean, people are thinking, and everybody's thinking about proposals for observables that would differentiate this from, let's say, a static or stationary extreme black hole.
Okay, great. Let's thank Achilleas again.